Good afternoon, everyone. First of all, let me thank to top leadership, Honorable Chancellor and Founder, Professor Sayyid Wasim Akhtar Sahab, Pro Chancellor Dr. Sayyid Nadeem Akhtar Sahab, Vice Chancellor Professor Javed Musawwar Sahab, Director HRDC Professor Sayyid Akil Ahmed, Dean Faculty of Science Professor Abdul Rahman Khan, to allow us to organize the faculty development program on current trends in theoretical and experimental research in physics under the aegis of Human Resource Development Center in Trigal University. Today is the second activity of the FDP lecture series. This course aims to refresh and update the current knowledge of teachers to address the rapidly changing educational needs and to encourage a multidisciplinary approach to teaching and research. The course is mandatory for all the faculty members of the Department of Physics. It is my honor to introduce the distinguished speaker and resource person, Professor Muhammad Mehendi Kalam, Department of Physics, Alia University, Kolkata, West Bengal. Professor Kalam obtained his PhD degree at Jadavpur University. He is a theoretical astrophysicist and working on modeling of neutron stars and wormhole from different sources of the universe. In 2010, he joined the Department of Physics, Alia University, Kolkata, where he is currently a professor of physics. Earlier, Dr. Kalam has served the Department of Physics, Netaji Nagar College for Women, Kolkata, as an assistant professor from February 2004 to September 2010 with the recommendation of the West Bengal Police Service Commission. Professor Kalam has various awards to his credit, such as Visiting Associate of Ayuka Pune, Visiting Associate of INSC Chennai, Tavas UNESCO Associateship Award, Trieste, Italy, Fellow of Royal Astronomical Society, London, UK, individual member of International Astronomical Union, Paris, France, member of European Astronomical Society, Geneva, Switzerland. He has more than 20 years of teaching and research experience and guided several PhD students. Let me invite Professor Mehendi Kalam to deliver the FDP lecture.
Okay. First of all, assalamu alaikum to everyone, and a
Walaikum
very good,
Assalam.
yeah, very
Walaikum
good
assalam.
afternoon to everyone, and also thanks Dr. Shah Alam for the introductions. And before starting off my lecture, I must extend my gratitude to the Integral University Authority and especially the Department of Physics for giving me this opportunity to deliver this talk in this FDP programs. So my topics is I will discuss today on the theory of relativity as well as the wormhole and the exotic matter. So I actually try to explain very lucid way, in a very lucid way, that what is the theory of relativity. That means that extends with the special theory of relativity as well as the general theory of relativity. And after that, I want to explain a very interesting things, that is the wormhole, and what are the research is going on wormhole. I think it will be very interesting for all of you. So now I will start with that. What is with the famous paradox that is called the twin paradox. So what is the twin paradox? All we know that the paradox is nothing but what happens if we put a formula of that and the result coming from that outcome of that formula, and if you compare with the reality, then it will be a havoc mismatch with that. So these kind of things are called the paradox, and in this situation we are discussing about the twin paradox. All we know that the twin the famous twin paradox deals with the two twin brother and sister. One is called Dick, another is called Jane, and Dick, both are in the 20-year-old, and these phenomena actually explained by the famous outcome of the special theory of relativity, that is called the time dilation. What is that? That means a moving clock ticks slower, right? that is nothing but the time dilation impact. So anyone thought that is that if a moving clock ticks slower, then why we are suppose we are moving with a car. So why not we see that this our clock is moving slower, ticks slower. So in that case, what happens in special theory of relativity, we always compare with the velocity of the object with the velocity of light. That means v by c. So all we know that the velocity of light in vacuum is nothing but a huge one. That means 3 into 10 to the power 8 meter per second. So in comparison to the car velocity is very very less. So v by c value actually tends to 0. So that's why we can't see any changes of the clock ticks. But if we consider a spacecraft, suppose, which is moving a very high speed, that means comparable to the velocity of the light, so in that case, this time dilation will take place. So what happens in the twin paradox is that I just want to mention that suppose Dick and Jane are 20-year-old, and Dick take a spacecraft to move to another planet which is nearly 20 light years away from our Earth. Then and Dick choose a spacecraft that spacecraft velocity is nearly 80% of the velocity of the light. So Dick will take how many time to reach the other planet. It will be simply the simple formula where with the distance equal to velocity into time. So in that case, the time comes out as 20 light years divided by the velocity of light in vacuum. That means the 80% of the velocity of the light. Then it comes out as nearly 25 years. So Dick will take 25 years measuring from the Earth's surface. So 25 years and coming back again to the Earth is another 25 years. So ultimately, total time expand is 50 years. So at that time, Jane stays in the Earth's surface. So what is the age of the Jane at that time? So 20 in the starting of this travel is 20 years, and after 50 years, so 50 plus 20, that means 70-year-old. But what we see that the Jane age is 70 years, but the Dick, who is coming back from other planet to the Earth, his age will be nearly 50 years. So he looks very, very young. So that is the called the twin paradox. So now, this situation is solved by using the time dilation. So the question arises: is it possible that this kind of phenomena will take place? Of course, it is possible, because we see that from the cosmic ray. Now the question is, what is cosmic ray? The ray which is coming from the cosmos, not actually ray, it is the particle, cosmic particle is coming from the cosmos. Among them is called the muon particle. Muon means the mu meson, but its speed is near about 0.998 into velocity of light c, and its average lifetime is only 2.2 microseconds. So now the question is, we get the muon particle from the Earth's surface. So what is the elevation? That means what is the altitude where this muon particle will be created? So automatically, at his lifetime is only 2.2 microsecond. So the distance will be s equal to v into t. V is 0.998 into 3 into 10 to the power 8 multiplied by 2.2 into 10 to the power minus 6. So it will comes out as 0.66 kilometers. So only 0.66 kilometers altitude the muon particle will be created. But in reality, what we see, if we check it, then we see that in reality the muon particle actually creates near about 10 kilometers from the height of the Earth's surface. So it will mismatch. So Newtonian mechanics can't fail to explain this one. So in this case, actually the time dilation gives the actual results. So what is that? We all know that if we consider that the situation is that we are measuring from the Earth's surface. So if we consider the muon particle, suppose a clock is fitted with that muon particles. So it's just like the spacecraft taking discs there. so the clock with the moving with the muon particles having the velocity of 0.998 c, so it comes here. So the clock at that moving frame with the muon particle will be the time dilation takes place. So the clock is ticks slower in that situation, and it comes out as the time comes out as here. This T naught is putting at 2.2 into 10 to the minus 6 divided by this 1 minus v square by c square is 0.998 into c. So it comes out as nearly 34.8 microseconds. So the lifetime of the muon particle, which the clock which is moving with that muon particle is 2.2 microsecond, but that same lifetime measured from the Earth's surface comes out as 34.8 microseconds. So from the Earth's surface, if we want to check which distance traversed by this muon particle in the altitude, then we will put this 34.8 microseconds multiplied with the 0.998 c, that comes out as 10.4 kilometer. So exactly it matches with the observational data. So we see that this special theory of relativity, that the time dilation is really takes place. Now, this time dilation actually comes from the famous theory of Einstein, which Einstein proposed in 1905. That is called the special theory of relativity. But Albert Einstein, in that special theory of relativity, one very important introduction of the dimension takes place. That is the time. Einstein take time as a extra dimension. So all we know that in the Euclidean geometry there are three dimensions, three spaces are there, x, y, and z, and Einstein take time as a extra dimension is there. So that's why this type of coordinate is called space-time coordinate. Many scientists thought that that the Einstein maybe thought in that way, that that we now all we are in these positions, and I am giving a lecture here. So is the time is there, and the space indicates that x, y, z, the coordinate is there. The before giving that lecture, I was in different places, and the time is also different. So maybe Einstein, maybe in his mind, that so time may be an important factor which is related to the space. So now the question is, why in this expression Einstein take this one, right? So as time is a coordinate, then automatically the distance between any 2 points, all we know that from the coordinate, simple coordinate geometry, the distance between any 2 points is what? So it is nothing but the square root of x2 minus x1 square plus y2 minus y1 square, z2 minus z1 square. And if the coordinates difference is very, very small, say then the distance between any 2 points is nothing but this one, del x square plus del y square plus del z square. If time is a coordinate, then only del t square will be sufficient. But why this c square is there? Because all we know that from the dimensional analysis, we can say that this del t square must be multiplied with the velocity square, right? So then in that case, the dimension is dimension is L square, and it will come the velocity. That means that distance by time. So it is nothing but the velocity, nothing but the dimension of L square. So now the question is, why this c? Why not any other velocity v? Because all we know that from the different frame to frame, the velocity of any particle will be changed due to that, right? But from the special theory of relativity, all we know that the velocity of light in vacuum will be the same in all inertial frame of reference. So it will be invariant. So as we are multiplying invariant quantity, so the distance between any 2 points must be an invariant one. Because in our physical example, we see that suppose we are taking the 3 coordinate system. So in that case, what happens? In the Cartesian coordinate system, the distance between any 2 points is nothing but dx square plus dy square plus dj square. But the same distance between any 2 points, if we are try to write in spherical polar coordinate system, then the expression will be d square equal to dr square plus r square d theta square plus r square sin square theta d phi square. So the expression is changed from the Cartesian to the spherical polar coordinate, but the distance between any 2 points will be unchanged. So that is the beauty of this invariant invariant expressions. So this del s, the distance between any 2 points, must be an invariant one. Now the question is again, why here is a minus? So minus actually comes as that this is space and time. So space and time is not will be placed in the same footing. That means if the space will be in a plane, then the time should be the perpendicular of that. So that's why we can take as the time as an imaginary one. So if the coordinate is taken as I c t, so in this case is del x, so I c dt, then the distance between any 2 point del s square, that will be this I c d del t whole square plus del x square del y square del j square. Automatically this I square comes out as the minus. So this is the signature cases. I'm not elaborating on that. So this is the basic phenomena of taking this del s square. This del s square called as a line element or the metric. So it is very important in considering the geometry of the space time. So this is metric is very important. I will discuss later. Now the question is, so oh, oh okay, just I have to mention. So all we know that the special theory of relativity actually follows earlier the Newtonian mechanics actually follows the Galilean transformations. So Galilean transformation is that, what is that? I try to explain here. This is the simply the static frame, and this is a frame which is moving with a constant velocity. All we know that this is, so it is an inertial frame of reference because it is moving with a constant velocity, right? Okay, so if any point we consider it is an x-axis, not y, it is the x-axis, it is x-axis. So suppose any point is p is here at this point. So what will be the coordinate? Coordinate is taken as, suppose we are considering Cartesian one, so x, y, z. So in that case, what happens if it is the x-axis? So that point p having the coordinate x, y, z from measuring from this s frame, and from the s dash frame, that same point will be x dash, y dash, z dash. So in that case, what is x dash? If it is the x dash, so this point x dash will be this one, right? Okay, but the same point, if it is the coordinate x, y, z, so x will be from this one. So automatically, and what is vt? Because velocity of this s dash frame is v, so in time t it will move to that total distance of v into t. So automatically x is equal to what? X comes as x equal to x dash plus vt. So x dash will be equal to x minus vt. And what will be y and z? There will be no change in the y and z direction because the axis is moving along the x-axis. So y dash equal to y, z dash equal to z. So this is the simplest Galilean transformation. Galilean transformation is that it is also the Newtonian mechanics we are applying everywhere in the three-dimensional space coordinate system, that x dash will be equal to x minus vt, y dash equal to y, z dash equal to z. Now why the problem arises? Problem arises when, if we consider, suppose the photon particle is moving. So that photon particle is moving when the velocity of the photon particle, according to this Galilean transformation, the velocity of the photon particle measured from the s frame comes out as c, and the velocity of that photon particle measured from the s dash frame is taken as c dash. So if it is so, here the expression is x dash equal to x minus vt. So if you take the time derivative both sides, then dx dash dt equal to dx dt minus v. So dx dash dt is the velocity of the photon measured from s dash frame. So it is c dash, and the velocity measured from s frame is c. So dx dt is c. So finally, for the velocity of the photon measured from the s dash frame comes out as c dash equal to c minus v. But what we see in the reality, we see that a photon velocity will be unchanged for any inertial frame of reference. So it completely violates that. So that's why we need a new type of transformations. Now, in another thing is that in the Maxwell's equation is also not invariant due to the same reason for that. So we need another type of transformation, not the Galilean transformation, but that transformation is called the Lorentz transformation. So by using this Lorentz transformation, this is the Lorentz transformation equation, and this exact comes out as this gamma. Gamma is a 1 by root over 1 minus b square by c square. So this is the Lorentz transformation. By using this Lorentz transformation, the most of the special theory of relativity formula are generated, and these are the others formula. I am just mentioning of that, that the mass is comes out as a relativistic mass, is m is gamma into n, m is there, and as well as the velocity addition formula is this one, and the energy is equal to gamma into mc square, and so on. So what is the main consequence of the special theory of relativity? Main consequence of special theory of relativity is that the mass energy equivalence. All we know that these mass and energy are equivalent. This E equal to famous E equal to mc square. This is the main consequence of the special theory of relativity. And also we have the light cone diagrams also, past, present, and future. There is an interlink between that. Always any event moves from past to present to future, and that is also comes from this special theory of relativity. Now, Albert Einstein tried to generalize the special theory, because special theory of relativity is only valid for the inertial frame of reference. So what will happen for the non-inertial frame? So Einstein have a thought on that, and but the calculations or the things is so complicated that such a brilliant scientist Einstein took near about 10 years to formulate this Einstein theory of general theory of relativity. So in 1915, Einstein the concept of the general theory of relativity, that is also valid for the non-inertial frame of reference. So what is general theory in lucid way? In the lucid way, I try to explain that is a concept of Einstein. There is no concept of the force as we see in the Newtonian mechanics. In general theory of relativity, there is no concept of force. Everything can be explained with the curvature of the space-times. So in general relativity, actually what happens according to general relativity, everywhere within our universe, there is always a space-time net is spreading everywhere. So and what happens if we put a heavier mass on their space-time, the space-time will be curved. In our practical experience, suppose we are taking a net is there, and we put a heavier body on that net, then what happens? What we see that the net is actually becomes the curve, right? The same thing is happened here. So that when a heavier mass actually curves the space times, so it will be it is explained very clearly by John Wheeler with a statement of that, a very interesting statement of that. That statement is that matter tells the space-time how to curve. Matter tells the space-time how to curve. What does it mean? So look at here. This is the space-time. So heavier matter comes here, and this space-time actually becomes curved. So if you put lighter mass, then the curvature will be smaller. If we put heavier mass, then the curvature will be much bigger. So matter tells the space-time how to curve, and the space-time tells the matter how to move. That means what is that? Suppose we putting a heavier mass in the space-time, so the curvature is there, and now in this position, suppose we are putting a smaller mass. So that smaller mass, what will do that smaller mass? That smaller mass actually moves through this curved space-time, because space-time is always a curve due to this heavier mass, and the smaller mass will have to follow this curved space-time to moving towards the bigger mass. So this is the general concept of general theory of relativity, which is very clearly explained with the statement by John Wheeler. So we see in the gravitational deflection of the light takes place due to this curvature of the space-time. So here is the sun. Suppose a light is coming from a star is there, and it comes to the earth, but due to this heavier mass, the light bends. So these are the consequences of the general theory of relativity, that the bending of light takes place. And it was proposed in 1917 by Albert Einstein, and Albert Einstein also calculated what will be the bending of the light when it passes near the sun, and it comes out as 1.74 arc seconds. So very, very small amount of bending is there, and that was actually calculated by applying the general theory of relativity by Albert Einstein, and the value is mind that 1.74 arc seconds. And actually, Arthur Eddington tried to do that. That Einstein's calculation is wrong. Actually, main objective is that many scientists thought that, so Arthur Eddington tried to see it experimental way. Then what is the bending takes place? And due to the solar eclipse in 1919, Arthur Eddington also the observational result indicates that the Einstein is the result is the perfect one. So the general theory of relativity actually proves that this phenomena is true. So in 1916, famous German scientist Carl Schwarzschild, by using this Einstein's theory of relativity, find a fantastic solution that is called the Schwarzschild solutions, and from there the famous Schwarzschild black hole solutions will get from that. So mainly Einstein's equation actually deals with the with the main equation, that is it is called the Einstein's field equation, and here left hand side gives the Einstein tensor, and the right hand side gives the energy momentum tensor. It is the interrelation between the matter and geometry which is the main objective of this general theory of relativity. So general theory of relativity, actually this Einstein tensor actually gives the geometry part. This Einstein tensor gives the geometry part, and this matter gives the energy momentum tensor. So these equation, Einstein's field equation, is the interrelation between this matter and the geometry, and from there we'll get the Einstein's field equations. And as I mentioned, one of the solutions of this Einstein field equations is nothing but the black hole solutions. I am just lucidly just mentioning that what is this one. So 3 types of black hole or 4 types of black hole till now. If the black hole having only the mass, that is called the Schwarzschild black hole. If the black hole having of course non-rotating of them having mass and the charge only, that's called the Reisner-Nordström black hole. And if it has the mass, charge and the angular momentum, that is called the Carr-Newman black hole. And if there is a charge absent, only the mass and the angular momentum, that is called the Carr black hole. And most importantly, it has the Einstein's field equation not only have the black hole solutions, but in the other solutions is there that comes from the wormhole. I will discuss elaborately of these topics of the wormhole. So in the black hole, what we see, we all know that the black hole having the huge gravitational attractions is that not even light can pass through it. And from this picture, we can understand that suppose the normal star, a light is coming there and it is spreading. And whenever it becomes a heavier one, neutron star, then light is bent towards this star. Slightly bending is there. More heavier neutron star bends more. And if it becomes a black hole, then light will come back to the black hole. That means not even light can pass through this black hole. And this black hole radius having the Schwarzschild radius is comes out that 2 gm by c square. If sun becomes a black hole, then its radius comes out as nearly 3 kilometers. So there are different types of black hole. I am just mentioning that there is a primordial black hole type whose mass is less than 10 to the 14 gram. And the stellar masses black hole is also there, whose mass is greater than at least 3 solar masses are there. Intermediate black holes are there, having 100 to 1000 solar masses is found in normal galaxies. Massive black holes is there, having 10 to the power 6 solar masses is there, mainly present in the Milky Way galaxy. And supermassive black holes is also there, 10 to the power 9 to 10 to the power 10 solar masses in the AGN. We'll see that. So a black hole having a singularity at the center, and it has the event horizon, and also we cannot see the singularity. That is called the cosmic censorship prevail. That means you cannot see inside of the event horizon. That is the most important point is also there. So where we can see the black holes, as I mentioned, at the center of the galaxies we can see, as well as for the binary stars we can see the black holes. So fast black holes is Cygnus X1 in the binary system. There are so many black holes now, hundreds of black holes are discovered. And uh, I want to just mention how we can detect this black hole is a simple phenomenon, because black hole, from the black hole nothing can coming out. So how we can identify that? These are binary stars, these are donor stars. Suppose black hole is there, so black hole having greater gravitational attractions is there. So the attraction takes place, the masses is coming from the donor star towards the black hole, and it moves in a cyclonic way. There's the gravitational attraction is so high that the rotational velocity at this position of the masses is so high that it creates an X-ray emission. So an abnormal X-ray emissions takes place in this situation. So scientists identified that there must be some heavier gravitational body is there which is hidden. So in that indirect way we can point out the black hole must be there. Now, as I mentioned, that the black hole is one of the solutions of the Einstein's general theory of relativity. So it has another solutions. It has another important solutions, that is called the wormhole. So if you see, so it is the simplest picture of a, it is a doctored photograph, of course it is a doctored photographs. These doctored photographs, one side is Sahara, another side is a New World. So now any people want to go from New York to the Sahara, then he or she has to take a long journey. But if wormhole exists, then any wormhole traveler or can move, take a simple steps to go to New York to Sahara. So it is if wormhole exists. I mentioned, repeat, if wormhole exists. Now the question is, so why we are if it is not exist, so why we are discussing with that? I'm coming. Now, what is a wormhole? So wormhole is an hypothetical tunnel that connects. Actually, it has two mouths and one throat is there. So the picture is this one. So two mouths is there, and there is a tunnel is there. So when a wormhole traveler can travel through this tunnel. Now it is a very important picture. Why important picture? So many thought that science fiction, in science fiction, the time machines, all we heard about the time machines. Now the question is, many thought that is it possible the time machine will exist or not? Okay, I must say that it is possible to create a time machine if we can detect wormhole. I am mentioning if we can detect wormhole. Why? Because wormhole is a very important tools to create a time machine. How this wormhole can be act as a time machine, I try to explain. Right? So this is the space time. So any light ray is light is try to move from point A to B. So light will travel the geodesic path. All we know that light has to travel the geodesic path. So light will move. This is the geodesic path. Light will move in this path to travel to from A to B. But if we connect this A and B through a wormhole, then in that situation, what happens? Any traveler moving from A, though his velocity is much less than the velocity of light, so special theory of relativity is valid, no problem. So the traveler can travel from A to B with a very shorter time than the light coming to that point. So in this way, this wormhole can be treated as a time machines. Now, if we can get the wormhole, so interstellar travel is possible. Of course, interstellar travel is possible. In this way, a famous Hollywood movies was shown that that is called the Interstellar, right? Interstellar, and that was Christopher Nolan is a director, and of course, Kip Thorne, famous Nobel laureate scientist, Keith Thorne is also in that preparation of that movie. So if wormhole exists, then interstellar travel, it is possible. So the name wormhole actually, what is the analogy of that? First, it was called by John Wheeler in 1915. The wormhole is the analogy is that if we take an apple, and the worm is placed at the top of the apple, now that worm wants to go from the top of the apple to the bottom of the apple. So the worm has two ways. One is that to travel through the skin of the apple. Another is that creating a hole from the top of the apple to move to the bottom of the apple. So wormhole traveler will be taking the second path. That means a worm is creating a hole to move from top of the apple to the bottom of the apple. So this is the analogy of this wormhole. Now, the brief history of the wormhole is there. As I mentioned earlier, that there is another solutions of the Einstein's field equation is there. Not only the Schwarzschild black hole, but as another solution. It was mentioned by Ludwig Flamm in 1916, and that solution is called at that time is called the white hole. That is, black hole absorbs everything and white hole repels everything. But Flamm is can't give any idea that if we consider a black hole entrance and the white hole exit, there's the Ludwig Flamm can't give any idea of that. It was done by Albert Einstein. The idea given by Albert Einstein and Nadal Rosen in 1933 that by taking the electric lines of force and such as the fundamental particle like the electrons, Einstein proposed that this kind of phenomena can be created, and that is called the Einstein-Rosen bridge. That is called the Einstein-Rosen bridge. And this Einstein-Rosen bridge looks like this one. Later, the same thing, John Wheeler called it as an wormhole. So there are mainly two types of wormholes are there. One is called the Lorentzian wormhole, another is called the Euclidean wormhole. Lorentzian wormhole is that wormhole which are dealing by the general relativity. We are using that in the general relativity, and semi-classic and the Euclidean wormhole are using by the particle phases. But we are very much interested in the Lorentzian wormhole as we are dealing with the general relativity. So in 1962, John Wheeler and Robert Fuller actually published a paper at first that shows that the Schwarzschild black hole is creating. But the problem is that the Schwarzschild black hole is very much unstable. And how it is unstable? If we see the diagram, you will see. So I want to, oh, sorry. So there is a movie is there. Is it it will act? Hello? So what happens? I just want to mention that. What is that? That according to this Schwarzschild black hole, what happens? This Schwarzschild black hole actually creating there. Okay, but as soon as it is creating, then automatically it will breaks here. Why breaks? Not even light can pass through it. So it becomes a unstable one. Why it is unstable? So I want to explain. Here is a huge space-time is there. There is a huge space-time is there. So what happens at the throat region? The attraction towards this throat region towards upward direction is so much high, as well as here is also the attraction towards the downward direction is so much high. So that's why in between these two big attraction in the two different ways, so this portion actually tear off. So that's why it becomes an unstable. Now the question is, if the wormhole becomes unstable, then there is no phenomena of getting a traversable wormhole. So we have to create a traversable wormhole. Then in that way we can use that. So for that, what happens? So basic idea is that to create a traversable wormhole. Now, to get a traversable wormhole, so we have to create a stable wormhole. That is the most important. So we have to stabilize that. So again, it is the idea of the Nobel laureate scientist Kip Thorne. Mind that in 1988, and Morris as well as the Thorne, the main idea coming from these two scientists, the Kip Thorne actually gives that idea. Idea is that suppose if we put a matter, peculiar type of matter, all we know that if we place a matter in that, it is not a real matter. That matter is called the exotic matter, and the matter having a peculiar property. What is the property? Or real matter having the gravity. So this exotic matter having a property of anti-gravity. That means, and also it has an energy which is called the negative energy. So at first I want to explain how this will act according to Kip Thorne. This is the mind that is the purely concept of Kip Thorne. That means Kip Thorne idea is that if you place a exotic matter at this region, an exotic matter having the property of repelling the gravity. So it is repelling the gravity. So what happens? Here is a huge mass actually repelling these portions of exotic matter in the downward direction, as well as this mass here, these huge masses, huge space times repelling that gravity in the opposite directions. Again, repelling gravity. So both having the opposite. So upper portion repelling this exotic matter in the downward direction, and the lower portion is repelling this exotic matter in the upward direction. So with these two basic different directions, forces actually balances at the throat regions. So this is the concept of Kip Thorne. Mind that. So Kip Thorne told that if we place exotic matter in this throat region, then the wormhole will be stabilized. And but the problem is that where we can get this type of matter, and this wormhole having a peculiar property, it has a negative energy, as well as it violates the null energy condition. Now the question is, what is the null energy condition? Well, we know that for the real matter, any real matter having always a positive density, and it has a positive pressure. So for the null energy condition is that the density rho plus p is always greater than 0. So this is the property of the real matter. But this exotic matter having the property of that rho plus p will be less than 0. So that is the that means this exotic matter violates the null energy conditions. Now the question is, so is it only a fantasy of that? No, not at all. Because according to the Matt Fisher, a famous wormhole physicist, told that during the several years of hard work, we cannot prove that wormhole doesn't exist, right? And so scientists thought that wormhole must be there, exotic matter must be there. As it is very difficult to get this exotic matter, scientists thought that we can minimize the using of that exotic matter to create a wormhole. If it that, and that was done by Matt Fisher and Shayonkar from Kharagpur IIT, Professor Shayonkar and Professor Naresh Dadich of the former director of IUCA. They have built an idea, they are given model where they can they create an wormhole by using a very small amount of exotic matter. And we also have given a model of that type by using a very small amount of exotic matter to create a wormhole, which is published in also PLB in 2006. Now the question is, so main problem is that where is that exotic matter? That is the main problem. Here I want to mention that in 1916, Albert Einstein gives the concept of general theory of relativity. And from the solution of the general theory of relativity gives a consequence that builds that the gravitational wave exists. Because gravitational wave is coming from the solutions of the Einstein's field equations. In 1916, mind that, till 100 years, we cannot detect gravitational wave. So it will take near about 100 years to detect the gravitational wave. Where is the problem? Problem is that the amplitude of the gravitational wave is so faint that at that time the technology is not so developed that we can detect the gravitational waves. So it will take near about 100 years to to get the existence of the gravitational wave. We now get it by using the LIGO detector and Virgo detector and so on. So, because the general theory, till now, no one can prove that general theory of relativity is wrong. And the solutions of the general theory of relativity, that is Einstein's field equation, gives the result of the gravitational wave. In the similar way, the wormhole solutions actually comes from that general theory of relativity, and it is a strong background of uh, of the general theory of relativity. So our technology is now not at that point that we can get that exotic, but the evidence is there. That is the most important point I want to mention, that the evidence of that type of present of exotic matter is there in our universe, in our world, I must say, because a possible source of exotic matter lies in the behavior of the quantum vacuum states as well as in the Casimir effect experiments. So I try to explain that in the experimental evidence is the squeeze quantum state. In the squeeze quantum state, what we see for the ordinary matter, this is the energy density is there for the ordinary matter. But in quiz quantum states, these expressions are getting. So what is the beauty of this? Beauty of this is that look at this region. This region, this is energy density. So in the negative energy density, but here is the some peak is there. To get that, the total energy must be conserved. But the point is that in that region, the energy density becomes negative. So we have to catch that negative energy at that particular positions. So our technology is not so developed today, but who knows, in the near future we can catch that negative energy at that point. And if we get that, so in that situation we can create the exotic matters. And another evidences is there is that in the Casimir effect experiment is going on in the Los Alamos, that it was proposed by Casimir in 1948 that if we consider two uncharged parallel plate and it is very close together, then the vacuum energy density calculated by Casimir in between this uncharged parallel plate comes out as negative. And scientists are trying to get this experimental result of this Casimir effect. Now, till now, near about 80% successful is there. It was going on in the Los Alamos. Now, what is our main objective? Our main objective is that to get a sophisticated geometry of the wormhole such that in near future we can create this type of traversable wormhole. And so scientists are trying to get that where is that exotic matter. That is the main objective of the research of the wormhole physics, is that to get this exotic matter, where in our universe, where is the source of that exotic matter. So scientists are trying to get that. So many research is going on till now, and we have also given a model by taking that exotic matter as a phantom energy. Phantom energy as a phantom energy, well, we know that is a one type of source of dark energy. So by taking that particular phantom energy as a source, that it may be a source of the exotic matter, by taking that we successfully create to construct a wormhole, and that was published in Physics Letter B. And here I want to mention what we are doing in our theoretical research is that this is the metric of the wormhole metric, okay, and this fr is called the redshift functions, that and this br, this is very very important. This is the safe function. That means this is the main responsible to get this wormhole like structures. This br is the main responsible is there. So to get a wormhole like structure, we have to prove these four conditions. We have to obey these four conditions. First one is that these redshift functions must be finite all over the values, and there will be no horizon takes place in the space time. And this also these safe functions br must obey the following. That means at the throat, always at the throat region there is a throat is there, one more throat. That means it is r naught. So at the throat r equal to r naught, b r naught must be equal to r naught. as well as b prime, that means the time the derivative with respect to distance, that is b prime r naught is less than 1, which is called the flare out condition, that should be satisfied. And also br by r, this br by r at r greater than r naught outside of the throat, that must be less than 1. And also the space time is asymptotically flat, that means that r tends to infinity, br by r tends to 0. And another very important point is also that there be must violation of the null energy condition, that means p plus rho must be less than 0 to get the wormhole structures. So these are the basic conditions have to be satisfied to get the wormhole structures. So what we are taken from there, we are taken the phantom energy as the source, and we have successfully successfully shown that all these conditions are satisfied to get that. Now another source can be taken, that all we know that another important dark energy source is the cosmological constant, because Einstein's introduced this cosmological constants, and scientists thought that as Einstein took this cosmological constant, it must have some impact on the matter distributions. So we also taken that this cosmological constant may be one of the source of the exotic matter, and by taking that we also give a wormhole model that is also published in General Relativity and Gravitations, and also we have done that. Now very interesting research is going on that we have also have some input on that research, that why not the dark matter may be one of the source of the exotic matter. So all we know that what is the dark matter, all we know that there is a huge region in our galaxy that is called the galactic halo region. The outer section of this galaxy, there is a dark regions are there, and that is the halo regions, and in that halo regions a huge amount of dark matter is there. So now the question is what is the dark matter? I just want to explain. It was actually first introduced, this concept of the dark matter having done by scientist Henrik Wirth. Wirth actually trying to explain the taking the observational data of the galactic rotational curve. Galactic rotational curve means what? The different part of the galaxy having different velocities. So Wirth actually try to see what will be the velocity of that different part of the galaxy's particles from the center of the galaxies. So it is from the theoretical point of view, if we consider circular motion, so the balancing equation is what? It is mv square by r equal to gmm by r square. So from there the velocity comes out as square root of gm by r. So this galactic rotation curve is just like this one, is just like this theoretical one, right? Root over gm by r. But what Wirth actually find from his observational data, that Wirth find that this galactic rotation curve looks like this one, just like the white light. So it becomes a flat one. So that's why this type of curve is also called a flat rotational curve. So now the question is, there is a huge gap is there. So Wirth thought that there must be a huge amount of non-luminous part is there. So that non-luminous part is responsible for this flat rotation curve. So later Zwicky actually gives the name of this non-luminous part as a dark matter. And this dark matter in our universe having near about 25% of is dark matter, and dark energy near about 71%. Only luminous part is only 4.4%. So huge amount of dark matter is there in our universe. Near about 25% is the dark matter. So scientists have thought that why not this dark matter may be an exotic matter, because we are trying to get the properties of the dark matter. We are still now searching what is the properties, different properties of the dark matter. All we know that the dark matter is very faint. There is no interactions with the electromagnetic interactions with the dark matter. Dark matter having the gravitational interactions is there. So scientists are trying that why not this dark matter can be taken as an exotic matter. And that was first done by Professor Farooq Rahman of Jadavpur University with his team, that the dark matter may be taken as an exotic matter, and there is some dark matter models are there, density profiles is also there, and they have taken the density profile, dark matter density profile, as the NFW, that means Navarro, Frank, and White dark matter density profile. And it looks like this one. This is the dark Navarro Frank dark matter density profile, and they have taken this dark matter density as a source of that exotic matter, and they have successfully can create a wormhole by using that. And later a famous dark matter physicist, that is Paolo Salucci, he actually proposed that that this NFW model actually of the dark matter is applicable for the exterior part of the galaxies is well known. But if we move to the interior part of the galaxy, then NFW model is not so valid. So according to Peter Salucci, he proposes a dark matter model that is called the URC model, universal rotational curve model of the dark matter model, and that was proposed by Salucci. And they have taken this model to try to explain that where this wormhole can be created or not, and they have also succeeded to create a wormhole by using this URC dark matter density profiles. Now we are seeing all these things. Now we thought that I, with my Iranian collaborator, during my visit of the TUAS UNESCO visit to the Iran, I thought that with my Iranian collaborators that why not we are checking that not for different galaxies. We know that the dark matter present in different galaxies. So we have the different galaxies data is there. So we have taken 50 different galaxy rotation curve data, and we choose 25 from the dwarf galaxy part and 25 from the huge spiral galaxy part. Huge masses are there, huge galaxies, spiral galaxies. So we have taken that data from the spark data, SPARC, spark data of the galaxies. We have taken from there. So 25 from the dwarf galaxies data, rotational curve data, and 25 from the spiral galaxies data. And by using, and we are taking the dark matter profile as a singular isothermal profile. It is the simplest dark matter density profile, that is the singular isothermal sphere profiles, and we have taken from that. Now the question is how our observational data will affect the shape functions. That is the most important, because shape functions is the most responsible to create the wormhole like structures. So look at here, this is the SIS density profiles, and this K factor, it is the velocity dispersion, and this density profile. And look at there, this is the V square halo, that means that comes from the observational part of the different 50 different galaxies, that comes from there, this V square halo, and that is related with this K due to this SIS density profiles, and this is K. So V square, the density profile, that is the galactic rotation curve data, the rotational data velocity is related to this K, and this K is related to these shape functions. So the shape functions is actually directly related with K, and K is directly related with the rotational curve data. So from that rotational curve data, we are successfully done this. So these are the different galaxies of dwarf galaxies, 25 dwarf galaxies data. Here is the calculated value of the dwarf galaxies for the K, and also here is for the 25 different spiral galaxies data, and from their values of K, we are successfully built the wormhole structures. And this paper is published in New Astronomy very recently. And here I must want to mention that here we will get this is for the dwarf galaxies. This for the dwarf galaxies, we gave this throat radius as 1 kiloparsec, and for the massive galaxies, this throat radius comes out as 10 kiloparsecs. Now the question is, as we are considering for the galactic rotation curve, that means at the center of the galaxy, it is well established that that at the center of the galaxy there is a supermassive black hole is there. Now for the dwarf galaxy, we see that the supermassive black hole, the radius is near about a very few, that means it will be 0.1 0.1 or 0.22 kiloparsecs. And for these dwarf galaxies, we see the throat radius comes out as 1 kiloparsecs. That means if at the center of the galaxy, if we consider the wormhole is a big wormhole, and it throat radius comes out as, if we center of the wormhole taken as the center of the galaxies, then in that situation it actually outside of the supermassive black holes region, the throat radius is 1 kiloparsec, and as well as the same thing for the dwarf galaxy, for the spiral galaxy is 10 kiloparsec. The radius of the supermassive black hole is nearly maximum is 1 kiloparsec for the spiral galaxies. So here is the throat is 10 kiloparsec. So we must say that one important thing is that as we successfully build the wormhole structures for these cases, we may thought that why not our nature actually creates that type of wormhole by taking the dark matter from the nature, by taking the dark matter from the nature. Why I am calling I'm saying that I want to give one true examples. What is that? We are in the Earth's surface. Earth is one of the planet of the solar systems. So our sun is one of the star. It is the simplest star of our universe. Not sun having not any extraordinary phenomena. It is a simple star. It is sun. Now the question is, we are in a galaxy that is called the Milky Way galaxy. So how many stars in our Milky Way galaxy? That approximately 10 to the power 11. 10 to the power 11 number of stars in our Milky Way galaxy. 10 to the 11 means you put 11 0 after 1, right? Now the question is, how many number of galaxies in our universe? So number of galaxies in our universe like the Milky Way is again 10 to the power 11. So now the question is, so in our universe, how many number of stars in our total universe? So that will be 10 to the power 11 into 10 to the power 11. That means of the order of 10 to the 22. So if we consider 10 to the 22 or 10 to the 23, again, we can understand this 10 to the power 23 is a very, very important figure, because all we know that if we go to the atomic scale, the order of the Avogadro number is 10 to the 23. And if we go to the large scale, it is again the number comes out as 10 to the 23. Another question is, we are in the Earth, is the planet of a simply one single star, solar system. The star is only sun. Like sun, we have 10 to the power 23 number of stars throughout our universe. Now the question is, so what part, how many part of our universe we know? A huge part is there which is unknown. So we can say that nature, as the nature creates the star, as the nature creates the different galaxies, so who knows, the nature also create the wormhole by taking the dark matter from taking the which is available in our universe. By taking the dark matter, wormhole is created everywhere else, but we don't have that technology to see that wormhole or to detect the wormhole. Thank you very much.
Thank you so much, Professor Mehendi Kalam, for this wonderful talk. You have started from the basic of special theory of relativity and moved to the advanced level of wormholes. So the participants have a few questions.
Yeah. Is how the hypothesis of the exotic matter is compatible with the Noether's theorem. No, that is the Noether's theorem actually gives the concept of the symmetry part, right? So as I mentioned, that exotic matter is a peculiar type of matter. It doesn't obeys the null energy conditions. So if these Noether's theorems is applicable, these Noether's theorem is applicable for the real matters, right? Okay, so exotic matter is not type of that real matters. So it is a peculiar type of matters which is violating the null energy conditions. So we have to see that. What is the nature of the quantum fields describing the exotic matter, fermionic or bosonic? No, these type of fermionic or bosonic, we that is not actually till now not mentioning it. It will behave like fermionic or bosonic. That is still now in our research is going on. But till now we haven't got that concept that the exotic matter is fermionic or bosonic. It is still going on. I don't know. Are photons really affected by? Yes, of course photon affected by otherwise we can't see the bending of the lights. So light is passing in a heavier mass, it will bend. So of course it affects the gravity. Can we drive Lorentz transformation equation from GTR? uh, it may be a problem for that. I don't see till now, but it may be drive. I think it may be drive from the GTR. We can get that Lorentz transformation equations, of course.
Okay. So
Thank you. Thank you.
I have one more question.
Yeah, of course, of course.
So can you please make some comments on the wormholes that affects the observable universe? I mean visible universe.
As I mentioned in the last at the last part of our of my lecture, that what kind of things actually we know. We are a very small region, very small region. Look at here that we are placing in our Earth, and that Earth is a part of the solar system, right? And the sun is one star, only one star. Whereas in our universe, there are 10 to the power 23 number of different stars. So the huge system, huge universe is unknown to us. We don't know where is going on and in which part of our universe is going on. We are very, very little we are knowing. So that's why we must say that because wormhole has a strong background of general theory of relativity. So that is the most important. That's why I mentioned about the gravitational wave. So our technology is not so developed today that we can detect this type of wormholes in our universe. So nature, of course, can create this wormhole by using, because huge amount of dark matter is spreading in everywhere in the universe. So by taking that dark matter, nature itself can create these wormholes.
Thank you so much. So okay. So let me again thank you, Professor Mehdi Kalam, for his wonderful talk, and hopefully we shall collaborate through research work in future, and we shall invite you physically at Integral University Lucknow,
Okay.
and also we hope we have some students exchange program between Alia University Kolkata and Integral University Lucknow. So
Yeah.
thank you so much again, Professor Mehndikula.
Okay. Okay. Thank you very much. Thank you very much. Should I leave?
Yes, please. Yes, please.
Yeah, yeah. I'm leaving. Okay.